Hello everyone. In this video, I'm going to discuss one interesting and important topic in VLSI design, that is pass transistor based logic design. So before understanding the pass transistor based logic design, so it is important to understand the working mechanism of a pass transistor, that is how NMOS and PMOS transistor can pass a logic 1 and logic 0. So in this example, I will show you the NMOS transistor, the passing of logic 1 and logic 0 for NMOS transistor, and what are the problems we can face. You can apply the same strategy for a PMOS transistor, and you will get the conclusion that whether PMOS can pass logic 1 correctly or it can pass logic 0 correctly. So let us see. Let's start from the NMOS transistor. So in this diagram, so just see that the NMOS transistor that acts as a switch. So it is called a pass gate or pass transistor. The gate terminal, the source terminal, and the drain terminal of an NMOSFET. And this is your parasitic load capacitor, a C load, and this node, we are saying the node voltage is Vx. Okay. So if we write the gate source voltage VGS, so that is equal to gate voltage minus source voltage. So that is nothing but gate voltage means we are applying logic 1. Let logic 1 is a 5 volt. For example, you can take any voltage, maybe 3.3 volt, minus source voltage, which is Vx. Because the source is connected to this node and the voltage is Vx. And at the drain terminal, initially we are connecting a logic 1, Vin equal to VOH, that is output high. So that is also 5 volt, because we are working with a logic 1 that is 5 volt and logic 0 that is 0 volt. At the beginning of our analysis, we assume that in the previous operation, this load capacitor C load was fully discharged, that is there is no previously stored charge inside the capacitor. That means at time t equal to 0, when we are going to start the operation, time t equal to 0, the capacitor is fully discharged, that is the node voltage Vx is 0. So at time t equal to 0, it indicates that the VGS is nothing but 5 minus 0, that is 5 volt. If we assume the threshold voltage of NMOS VTN equal to 1 volt, if we assume this, so VGS is greater than VTN, so the NMOS, of course it is on, because this is the condition. The threshold voltage of NMOSFET is less than this one, applied gate voltage, VGS greater than VTN, so NMOS transistor will be on. So when the transistor is on, now see this node, the drain is at 5 volt, and this capacitor, the node X, is at 0 potential. So the capacitor will charge. So one current will flow and the capacitor will charge. So when the capacitor charges, so all of you know that voltage across capacitor will increase exponentially following this type of graph with respect to time. The voltage across capacitor, in this case it is Vx, it will increase exponentially. So when the voltage across capacitor Vx increases, so let us see here, when the voltage across capacitor Vx increases, what will happen? The VGS value will fall. Okay. Because VGS equal to VG minus of Vs, that is 5 volt minus of Vx. So VGS will fall. And the minimum value of VGS required to make the MOSFET on, just to keep on that NMOS on, so that will be equal to VT. That means VGS minimum, that is equal to 1 volt, so that is nothing but the VT on to keep NMOS on. But if the VGS less than VTN, the transistor will be off and no such discharging will take place. So now we are going to calculate what will be the value of a Vx so that the VGS value will be 1 volt. Below that, the VGS will be less than 1 volt. Now see, when Vx equal to 4 volt, when Vx equal to 4 volt, 5 minus 1, 4 volt, then VGS is 5 minus 4, that is 1 volt. Okay, that is Vg minus of Vx. So when Vx will try to increase from 4 volt, because the capacitor starts charging, it charges, then what will happen? The VGS value will be less than 1 volt, okay, and the MOS will be off as per the condition, this condition. MOS will be off and no further charging takes place. So at the output node, the maximum voltage we are getting, so that is equal to the Vx, that is this load capacitor will charge how much? Up to 4 volt. That is, we can write VOH minus of VDD. Okay. So we are not getting the complete 5 volt at the output. The maximum voltage we are getting, the VOH, that is 5 volt minus of, sorry, 1 minute. So the output we are getting VOH minus of VT, not VDD, VT. Okay. So VOH is equal to 5 volt minus 1 threshold voltage drop. So that is 4 volt max we are getting at the output side. I think it's clear to all. The same explanation we can apply. So this is for logic 1. When we are applying a logic 1 at the input of a pass gate, the NMOS pass gate. So the output we are getting 4 volts. So NMOS cannot pass logic 1 correctly. So let us see. If I apply a logic 0 at the input of NMOS transistor, then what will happen? Okay. So if I apply the same explanation here, okay, let's discuss here. So here Vin equal to 0 we are applying. Okay. And here you can see the logic 1, same 5 volt we are applying here. And the C load in the previous cycle, that the C load was fully charged up to VOH, that is 5 volt. Now Vin equal to 0. Okay. And sorry, it's not 5 volt. The C load was charged because maximum it can charge up to 4 volt. Okay. And when you are applying a logic 1 equal to 5 volt here, what will happen? The transistor will be on and there is a discharging path. Okay. The current will flow in that direction. The load capacitor will discharge. As a result, the value of Vx will fall because the capacitor discharges. Voltage across capacitor will fall. And when the value of Vx falls, so as a result, the value of VGS, the Vg minus of this one, value of VGS means this voltage minus of this voltage. When this voltage reduces, the value of VGS increases. Okay. So the capacitor will completely discharge up to 0 because when Vx equal to 0, the value of VGS will be 5 volt and the MOSFET is on. So we are not facing any problem at the time of discharging. So we can say that, we can conclude that when during logic 0 transfer, we are not facing any problem. The problem we are facing in logic 1 transfer, here the maximum output we are getting 4 volt, that is VOH minus of VTN. But for logic 0 transfer, the load capacitor can be completely discharged up to 0 volt. So we are not facing any problem. Let's come to some other example. Suppose the bus transistors are connected in cascade. So what will be the output? So from previous example, we know that, so the input is a 5 volt, that is logic 1. Okay. So what will be the output? So if we assume that all transistors having a uniform threshold voltage of 1 volt, for example, so here the maximum output will be how much? 4 volt. Okay, so here the 5 volt input is there. So maximum output at node X, you will get a 4 volt. Similarly here, it will be Okay, just a minute. Here it will be how much? 4 minus 1, that is 3 volt. Oh, sorry. Yeah. In the second case, now see, so here you are getting 4 volt. So in the node Vy, how much it can transfer as per the logic? We know that it can transfer VOH minus of VTN. That means the maximum voltage it can transfer 4 volt. What is our input voltage? 4 volt. So it can easily transfer that and the output will be 4 volt. Now here in the same case, here input is 5 volt. So threshold voltage is 1 volt. So it can pass maximum how much? 5 minus 1 VT. That is threshold voltage, that is 1 volt. The 4 volt, 5 minus 1, 4 volt. So here also the output you will get 4 volt. The same case, output voltage you will get 4 volt. So conclusion is that when multiple pass transistors are connected in cascade in this way, okay, and if the same gate voltage applied and if all are having the uniform threshold voltage, then we can say that the output will be, final output V naught will be equal to this voltage, where this is V in minus of the threshold voltage, this one. Because if the gate voltage is 5 volt, so the maximum allowable output is 5 minus Vt, that is 5 minus 1, 4 volt. First stage, so it can pass up to 4. Second stage, 5 minus 1, 4, it can pass 4. So available input voltage 4 volt, so it can easily pass this one. Similarly, here it will get 4 volt, here also it will get 4 volt. But here the situation is a little bit different for this case. But here come with the same example, VDD is 5 volt, so here also it is 5 volt, so here also is 5 volt, and we are talking about VT that is equal to 1 volt. So here 5 volt, so VDD here also 5 volt. So here how much it can pass? So 5 minus 1 VT, so 4 volt. Okay. Now in the second stage, now the gate voltage is 4 volt. So how much it can pass? 4 minus 1 VT. That means 3 volt it can pass. Input is 5 volt, okay. But the output you will get how much? This one, the gate voltage, 4 volt minus of 1 threshold voltage. So 3 volt. Similarly here, 2 volt it can pass. So that means the final output you are getting V03 equal to VDD, that is 5 minus 3 VT, that is 2 volt. So multiple threshold voltage drop takes place. See, if we compare this one with this one, so here only one threshold voltage drop takes place, V minus VT, but here how much? 3 times of VT. So multiple threshold voltage drop takes place. As a result, so the previously the VDD VOH that was limited to VDD, that was a 5 volt. Now at the output here we are getting V0, that is V03 we can say, that is 5 minus 3, that is 2 volt. Now our output level became 2 volt. So that is not acceptable actually, because you know we are talking about logic 1, that is as per our previous definition, logic 1 is 5 volt, but here we are getting only 2 volt. So that is not acceptable. So multiple threshold voltage drop takes place if the output of a pass gate is connected to the gate input of another one logic gate. So this type of structure is not desirable. So whenever you are working with the pass gate, the desired structure will be like this. Now, let us see how we can implement the logic using pass transistor. There is a uniform framework for this. See how we can implement it. So before going to the logic design, the first step is you first go for the truth table. Okay, so we are here we are talking about a two variable Boolean expression a, b, and y, which is a NAND gate. So let's design the truth table. Okay, so this is the first step, the beginning step. Then from the truth table, you need to establish some relation. Now, what is the observation? See, when a equal to 0, the observation is the observation between b and y. So here you can see y equal to a bar. Okay, y equal to a bar. See here, if a0, y1, a0, y1, so we can write this. Okay, or also we can write when a equal to 0, y equal to 1. That is also correct because y is always 1. It is independent of b. Okay, whatever the value of b is, either 0 or 1, the y is 1. Or another way we can write y equal to a bar. When A equal to 1, then find, see, when A equal to 1, Y is a complement of B. When B 0, Y 1, when B 1, Y 0. So Y equal to B bar. So this is the relation. Okay. Then we have two input, two pass gate. We are using NMOS because you know NMOS is preferred over PMOS due to their high electron mobility. So we have a control signal of A. So here A equal to 0, Y equal to A bar. So when A equal to 0, we are working with a NMOS transistor. Okay. So A equal to 0 means A bar will be 1. Okay. So A bar will be 1 because we need to apply logic 1 at the gate input of N MOSFET. So A bar will be 1. So this transistor gate input A bar. So this transistor gate input will be A. So basically here we are placing the control signal, which is A in our case. Okay. So when A equal to 0, Y will be A bar. So this is our input. And when A equal to 1, Y equal to B bar. Now let us see. When A 0, so this transistor will be off. So A bar will be 1. So this transistor is on. So output will be which one? So this logic, this input will be at the output. Similarly, when A1 means this transistor will be on and this one will be off because A1 means A bar 0 and output will be which one? B bar, because Y equal to B bar, we derive it from this truth table, Y will be this one. So this is the working mechanism of a NAND gate, and similarly you can implement any two variable Boolean expression using the same structure, only those signals will change. You can take A as a control signal, and if you want you can also take B as a control signal, okay, and you can establish one relation between A and Y. That is also same, that is true, you can do that. But remember that this structure will also follow the same, whether A is on or this transistor is on or this transistor is on. If the input is a logic 1, the output you will get, that is VOH minus of 1 VT. That means one threshold voltage drop will take place. If your input is logic 0, then it is not a problem, because we don't know here the input is logic 1 or logic 0, because it is A bar. It will come from his. A may be 0, may be 1. Okay, similarly, B value may be 0, may be 1. Suppose in this case, B may be 0, may be 1. So B bar may be 1, may be 0. So when B bar is 0, no problem. At the output, you will get 0. But when B bar is 1, then output you will get how much? VDD minus 1 VT. One threshold voltage drop will take place. And if you want, you can connect one CMOS inverter to restore the logic. So output will be, that means here you are getting NAND. So output will be complemented, and so sometimes it is used to restore the logic level. So CMOS inverter will restore, that is here whatever if the 4 volt is coming, so it will be treated as input high, so output will be 0. In that way, it can convert. Now, if we go for some other example, the same concept you can apply for a NOR gate. So first go for truth table, the truth table of NOR gate. Then see when A equal to 0, the relation between B and Y equal to B bar. When A equal to 1, actually this one, Y equal to A bar. See, the structure is same as before, A bar, so we are not going to change it. Just update the input. When A equal to 0, A0 means A bar will be 1, and input is B bar, and here input will be A bar. The same design. Another one, two input variable, XOR gate. Go for the truth table, go for the observation. When A equal to 0, Y equal to B. When A equal to 1, Y equal to B bar. This is the observation. The same structure, Y equal to B, Y equal to B bar. But see, one interesting thing that although we are talking about the two input variable, if you go for a higher number of inputs, okay, so then the logic design using pass transistor, it requires less number of transistors. That is one of the major advantage of this pass transistor based logic, although the drawback is the threshold voltage drops takes place. Similar to your two input variable, so you can also implement the three variable Boolean expression. And another one thing, this structure is nothing but a 2 plus 1 max. So that means if you take this one is instead of A, so if you take A as a S, Okay, the select line, and this is your I0 and this is your I1. Okay, and this is S and this is S bar. So the working mechanism is just like the 2+1 marks. So pass transistor based logics are basically, it is called the switch based logic or multiplexer based logic. That means the circuit is implemented in form of multiplexer. We are working with the two variable Boolean expression, so it is basically 2+1 marks. Similarly, if you go for a three variable Boolean expression, let for a full adder or any three input logic gate, so then you have to go for 4+1 marks. So then the structure will change, and here actually at the input, since it is 4+1 marks, the input stage 4 pass transistor, then another one 2 pass transistor will come, etc. So this is all about pass transistor based logic using NMOS pass transistor. So hope it will help you to understand the logic design principle using this one. And for further study and explanation, you can visit this one.